Alright, welcome back. We're now about to go into topic 10, which is titled Chemical Reactions in Aqueous Solutions. Notice the chapters that it aligns to in the textbook, so if you need additional information, you can always go to those sections and look up that information. Topic 10 goes right in line with topic 9. Topic 9 we talked about chemical reactions, and then topic 10 is just going to be specific about aqueous solutions. So to get started, we're going to look at section 1, which is talking about types of solutions and specifically what electrolytes are. Alright, so let's review real quickly what a solution is before we start talking about types of electrolytes. So a solution is simply a homogeneous mixture. So it's uniform throughout. There's no differences between the entire mixture, but it is a mixture. Solutions typically get thought about as being liquid, but they don't always have to be. Solutions could be gaseous or they could be solids, but primarily we're going to be looking at liquid solutions. And so an example of a liquid solution would be something like salt water. So when you think about salt water, which is obviously just table salt, sodium chloride, and water, there's two parts to it. So there's the solute, which is the substance that's being dissolved. Typically, this is going to be lesser in quantity. And then there's the solvent, which is the dissolving substance. It's what's doing the dissolving. And this is typically greater in quantity. If you think about our saltwater example and start thinking about what each part is, the solute would be the table salt, the sodium chloride, and the solvent would be the water. And together, the solution is a combination of the solute plus the solvent. Now, it doesn't always have to be one solute and one solvent. Sometimes there could be multiple solutes, but that's the idea. The solution is the combination of those two things. How this happens, how something comes to be a solution, is a process known as solvation or hydration. So thinking about that table salt example that we just talked about, what actually happens when you put sodium chloride, or in this picture right here, potassium chloride, what happens when you put that in a substance such as water? Well, what ends up happening is the water molecules are going to come in and they're going to surround the solute that's being dissolved. And what's going to end up happening is the water molecules are going to actually pull out the parts of the ionic compound, and that's how you end up getting your ions. Specifically, the negative chlorine, in this example it's chlorine, but the negative ion is going to end up getting pulled out by the positive hydrogen. So you can see it's the white atoms that pull out the chlorine, the white atoms being hydrogen. And then the positive ion, in this example potassium, end up getting pulled out by the negative oxygen, because remember, oxygen has a slightly negative part because it's polar. But that's the idea. That actually is what's happening. So when you take your salt water, or your salt, and you dissolve it in water, that's what's happening. It's the process known as solvation. So on that topic of electrolytes, there are two types of electrolytes, two types of solutes. There's electrolytes and there's non-electrolytes. You've probably heard of this term before, electrolytes, like Gatorade, but electrolytes are simply substances that when you dissolve them in water, they're going to conduct electricity. Why? Why do they conduct electricity? Because they produce ions. So an electrolyte is something that, if it dissolves, it produces ions. So an example of that is sodium chloride, like we just talked about, or table salt. So when you put that in water, what ends up happening is you end up getting the production of ions. A non-electrolyte is a substance that when you dissolve it in water, it's not going to conduct electricity. Why is that? Because it doesn't produce ions. An example of that would be like sucrose, which is your typical table sugar. So if you dissolve sugar in water, it's going to break down into smaller molecules, but it's not going to produce any ions. And so because of that, it's not considered an electrolyte. Now, how can you test for this? Well, in the lab, what we could actually do is you could actually take beakers of your substance that you wanted to test, and we could actually put a light bulb in there that has its electric prongs in the solution. And what happens is, if the actual substance produces ions, meaning it can conduct electricity, the light bulb will turn on. You notice in this example right here, the light bulb does not turn on. And if you zoom in, the reason why is you can see there's no ions in solution. It's all water. So water itself does not actually produce electricity. So you may have heard when you were younger, like, don't swim in a swimming pool when there's a lightning storm. A lot of people think it's because of the water. And it's not because of the water, it's because in the pool there are ions that are dissolved. So it's the ions that conduct electricity. So theoretically, if the pool was pure water, it would not conduct electricity, and you would therefore be safe. I definitely wouldn't suggest that, but the theory is that. In all reality, most solutions end up having ions in there. So you can see here, it's really tiny on the screen there, but you get your positive ion, you get your negative ion. Okay, so that's going to light the light bulb up. Same thing over here. The reason why these two examples here light up is because there are ions present. Now you obviously can see there's a difference. This light bulb is shining kind of dimly. This one's shining bright, kind of like a diamond. Why is that? Well, pictorially, you can see the difference. In this solution, there's not many ions. In fact, most of the molecules actually remain intact. They don't ionize. Okay? It's only a few ions that end up getting produced. So there's still ions, but just not a lot. In this example, all the way to the right, you can see most of your substances have all turned into ions. And so you can see there's a difference between these two. Key thing, though, our picture on the left was a non-electrolyte. The picture in the middle as well as on the right are electrolytes. This is a good opportunity to talk about acids and bases. Acids and bases are considered electrolytes. Why is that? Because they produce ions. But let's be more specific. Acids. What ions do acids produce? You might remember acids are going to produce the hydrogen ion. So acids are electrolytes specifically because they produce hydrogen ions. And bases are also electrolytes. Why? Because they are going to produce the hydroxide ion. So that'll be good to know when we get to the part about acids and bases. But I wanted to talk about how acids and bases are part of that electrolyte category. One thing I want to point out on this slide, other than the fact that acids and bases are considered electrolytes, is I do want to point out the strong acids. There are 7 strong acids. And the reason why they're considered strong is because they are going to ionize 100% or near 100%. Meaning if you drop any of these 7 substances in water, they're all going to ionize. You're going to end up getting a situation that we had here on the right. And so it's good that you have to know these 7. You need to memorize these 7. You have hydrobromic, hydrochloric, and hydroiodic acid. And then you have nitric acid, perchloric acid, chloric acid, and then sulfuric acid. There's really no unfortunate clever way to remember that, other than you're just going to have to know those 7. Notice these ones right here are binary acids, meaning that they're just hydrogen and an element. And notice what element is attached. They're all halogens. The only exception, the only halogen that's not listed is HF. Notice that's not listed there, but that might be a good way to help you remember. Other than that, any other acid is going to be considered a weak acid. And that means it's only going to ionize slightly, okay? Meaning it's going to produce some ions, just not fully. We'll come back to that. Here's another, just to kind of wrap up to what we've been talking about. How can you tell that something is a strong electrolyte versus a weak electrolyte? Strong electrolytes will ionize almost completely. In other words, they will produce a very large number of ions. A weak electrolyte is only going to produce a small amount. It does produce some ions, but just not that many. Now, if I give you the picture view, like you see here, it's easy to tell which one's which. But what if I don't do that? Okay, what if I give you just the formulas? How do you know if something is considered a strong electrolyte? Well, there's 2 ways that something can be considered a strong electrolyte. The first way is if it's a water-soluble ionic compound. Okay, and that's key, water-soluble. So, number 1, if it's an ionic compound, it has a good possibility of being a strong electrolyte. But if it doesn't dissolve in water, meaning it's insoluble, then think about it. It's not going to produce any ions or negligible amount. And so it's not going to be an electrolyte. So you have to make sure it's water soluble. And how do you know that? You check the solubility rules that we learned in topic 9. So what's a strong electrolyte? First thing, check to see if it's an ionic compound that's water soluble. But the other way it could be a strong electrolyte is if it's one of the 7 strong acids that we just went over a few slides ago, right? So if it falls under either of those 2 categories, it is considered a strong electrolyte. Okay. A weak electrolyte, just to revisit that, a weak electrolyte is something that is going to produce ions, but not fully. And why is that? Because weak electrolytes do not, at any one time, you don't have all ions. So let me give you an example. Let's consider this really basic example down here. You have A plus B2 is going to make the compound AB2. Very general example, right? You see this double-headed arrow here? that means it's an equilibrium. It's a forward and reverse reaction. Usually it's denoted by this arrow notation instead, but the idea there is that the reaction is actually going in both directions. Okay, think about like if you're at an airport, you've got people going to their airplane, while at the same time people are returning from the airplane, right? So you got people that are departing and people that are arriving, and it's always this constant back and forth. There really isn't ever at one time everyone going in one direction. And that's the idea behind a reversible reaction. And so think about this picture right over here, okay? Here's your product, right? So I can see our AB2 product, but then you also have reactants kind of floating around here. And the idea is at any one time while this reaction is taking place, you're never going to have everything in here be AB2. While some of these might combine to make the product will also break apart into the reactants. That's the idea behind a reversible reaction. And so think about it. If that's happening, is there ever a time that everything would be ions? No, and that's why it's considered a weak electrolyte. Because while some things are turning into ions, ions are reforming to create the reaction. And unfortunately, because I'm doing a screencast, this is actually an animation. It's not showing right here, but if you look at the Google Slides in Canvas, you can see that this animation, you can see that demonstrated. Okay, so here's a good review. We've got a few minutes of this section left to wrap up. This is a good review of how you can tell if something is a strong electrolyte, weak electrolyte, or non. The very first question I ask myself is it a water-soluble ionic compound? Yes, then it's probably a strong electrolyte. The word probably is in there because there are a few exceptions, but basically if it's a water-soluble ionic compound, it's going to be considered a strong electrolyte for our intents and purposes. Well, what if it's not an ionic compound? Okay. Well, ask yourself, is it an acid? Because if it is, it could be one of the 7 strong acids, in which case it would also be a strong electrolyte. But what if it is an acid, but it's not one of the strong ones? Then it would be considered a weak electrolyte. Okay, well, what if you ask yourself if it's an acid, but it's not, right? Well, then ask yourself, is it an NH3 or another molecular base? NH3 is the only one, honestly, at this point, I would care for you to know. NH3 is considered a base. Well, if it's considered a base, then it is a weak electrolyte, because remember, bases are electrolytes. And if you answer no to all those questions, then it's probably a non-electrolyte. So with the last few minutes we have, let's do some examples. And I'm going to go back to that flow chart in a second here. Okay, so in example number 1, we have some compounds listed here, right? And so we have magnesium hydroxide. And so that's an ionic compound, right? It's an ionic compound. So let's go look at my solubility rules and see if magnesium hydroxide is water soluble. And so if you look at your solubility rules for hydroxide, you'll notice that hydroxide containing compounds are insoluble. There's a few exceptions, but magnesium hydroxide is not one of them. So even though magnesium hydroxide is an ionic compound, when you drop that in water, it's not going to dissolve. And so this would be a non-electrolyte. Sucrose. Sucrose, is it an ionic compound? Okay, no. Is it an acid? No, because it would have hydrogen at the front of it. Is it NH3 or another base? No. And so because it's no to all of those, it's a non-electrolyte as well. And we actually talked about that earlier. Potassium citrate. Okay, you may not know what citrate is, right? You're like, oh gosh, I don't know what that is, right? But notice it has potassium at the front. So potassium citrate is an ionic compound. And so ask yourself, is it a water-soluble ionic compound? The answer is yes, it is. And so in this case, it would be a strong electrolyte. It's going to dissociate all the way. Ascorbic acid. Notice it is an acid, but is it one of the 7 strong acids? And it's not. So it is an electrolyte, but it is a weak electrolyte. Perchloric acid. It is an acid, and it is one of your 7 strong acids. And so this would be a strong electrolyte. Sodium nitrate is an ionic compound, and this is a water-soluble ionic compound. So this is a strong electrolyte. It's going to dissociate all the way. Ammonia, NH3. Okay? Ammonia is not ionic compound, and it's not an acid, but it does fall in this molecular base category. And so since it is a base, it is going to be an electrolyte, but it's going to be a weak electrolyte. And then finally, hydrosulfuric acid is an acid, but it is not one of the 7 strong ones, and so it is weak.